welcome back. This is lecture 5. So in the previous lecture, in lecture 4, we discussed mostly about how to take a nonlinear circuit, or rather how to take a nonlinear element and do a linearization of that element, right? Why do we want to do a linearization of the element? Because we saw that using the magic of Taylor series, we could break the incremental voltages and the currents through the nonlinear element into linear and nonlinear terms, and under the condition that the nonlinear terms are much smaller than the linear term, we could neglect the higher order terms, and we could essentially say that whatever nonlinear element we have to deal with, under certain operating conditions, we can linearize it. And what is so holy about this method of linearization? The beauty of this method is the fact that it will help us to do a linear circuit analysis, because all our knowledge of handling circuits, right? All our knowledge of handling circuits work efficiently as long as we can transform them into some sort of linear equations, right? So, and in the road to doing that, what did we do? We took an example of an arbitrary nonlinearity, and we said that if the voltage across this is Vn, the current through this is f of Vn, right? This is Vi, this is RL, and what did we say? What were the steps? The step 1 was to find out the quiescent currents and voltages. That is, we do a numerical simulation, or we do a numerical analysis, or we do a graphical analysis. So we find out the quiescent currents and voltages, and let's say after doing some numerical or graphical methods, we could find that for a certain value of Vi, the current through this network was I sub n, and the voltage across this device was V sub n, which means the voltage across RL is Vi minus V sub n, which is nothing but In times RL, right? So we do a numerical analysis to find these values, right? So perform a numerical / graphical analysis to find In and Vn. Okay, so now that we have found, what was the next thing? Next thing that we said was, if my input was, let's say, Vi plus delta Vi, where delta Vi is a small increment, right? Then I could, in principle, find out the relationship between the current, the incremental current and the incremental voltage. Let me use a different color here. So let's say I had plus delta Vi, then obviously there will be an incremental voltage across a nonlinear element, and the current that was In to start off will now change to In plus delta In, and now the whole focus shifts to finding out this delta V, finding out delta Vn and delta In given we have delta Vi, right? So now the focus shifts there, and in order to figure it out, what should we do? So let me move this part here. In order to do that, in order to find out the relationship of the incremental quantities, what we do? We replace the nonlinear element with a resistor. What is the value of the resistor? The value of the resistor is 1 over del F 1 over del F del V around the operating point Vn. What happens to the resistor RL? This RL remains RL. What happens to the input? Note that since we are concerned about the delta Vi, the input effectively becomes delta Vi, correct? So this current that we will have after solving for this network will be delta In, and this then the voltage drop that I will get across the linearized version of the nonlinear element will be delta Vn, right? So this essentially was the crux of the entire lecture 4, right? Okay, so now that we have delta Vn and delta In, right? So let me write down this step also. So this step was the second step as in replace all elements in the network with their incremental equivalent, right? So this network here is the incremental network, right? So now that we have gotten the quiescent and the incremental, so what is the final step? The final step is to find out the total. Final step is to find out the total INV, right? Not only the increment. So essentially, what are we after? We are after if the input is Vi plus delta Vi, and the network consists of an actual nonlinear element, right? If this is Vn plus delta Vn, right, and this current is In plus delta In, right? So what is the final solution? The final solution will be to find total voltages and currents for input Vi plus delta Vi. We need to add up the responses from the quiescent and the incremental networks, right? So essentially we have found Vn and In, right, from operating conditions, and we have found small delta Vn, or rather delta Vn and delta In from the incremental conditions, right? We have found capital Vn, capital In from this network, right? We have found capital Vn, capital In from this network, and we have found delta Vn and delta In from this network, right? So once we have found these two, what we need to do in order to find the total, we simply need to add them up, right? I missed a step here. I didn't evaluate delta In. What is delta In? So I know that delta In is delta Vi by RL plus this incremental resistance, right? What is that incremental resistance? That is 1 over del F del V evaluated at Vn, right? So once I know that this is delta In, what is my total current? Total current is equal to In plus delta Vi by RL plus 1 over del F del Vn evaluated at Vn. Okay, fine. Okay, great. So again, at the cost of repeating myself, what did we do? What did we do in order to figure out the solution of this network? This becomes a three-step process. One, find out the quiescent currents and voltages, or the operating currents and the voltages, using graphical or numerical methods. Step 2, linearize the circuit, right? Sketch the incremental network. What is the incremental network? The incremental network is nothing but the linearized version of the nonlinear. It's the same network where the nonlinear element has been replaced with the linearized version, and all the sources have been replaced with their incremental equivalent, and then you find the incremental currents and the voltages from the incremental network, right? And it is easy to find because this incremental network is fully linear. So essentially now you end up having two quantities. One is the quiescent, or the operating currents and voltages. Another is the incremental current and voltages. In order to find out the total, you just simply add them up. And what is so great about this? The great thing about this is that now if delta Vi changes, right? If delta Vi changes, if delta Vi is, let's say, 1 millivolt, I just simply replace 1 millivolt instead of delta Vi. If delta Vi becomes 10 millivolts, right, I replace 10 millivolts instead of delta Vi. If delta Vi is 100 millivolts, I replace 100 millivolts in place of delta Vi, and I do the incremental analysis again. So you have to do the quiescent analysis once, and at the cost of doing the quiescent analysis once, you are able to do all the incremental analysis in a linearized fashion, right? So that is the power and the strength of this of this method. But note that you have to be slightly careful. You cannot do this for any values of delta Vi. Why? Because this linearized version of incremental equivalent is only valid when you can neglect the higher order terms. And if delta Vi keeps on increasing, the higher order terms for the Taylor series will be non-negligible. So in essence, there is a maximum limit of delta Vi, right, beyond which these incremental linearized models are valid, right? And in this course will not breach that limit, but it is always instructive to keep that at the back of your mind. And there is one more jargon that is used to refer to this incremental linearized model, right? So that is called a small signal model, right? And by definition, what is small signal? So when the higher order terms of a Taylor series of the Taylor series of the nonlinear element can be neglected with respect to the linear term, right? We call the linearized model a small signal equivalent or small signal model, right? So from here on in, we will use this term small signal linear or linearized incremental model interchangeably. Okay, so if you open up textbooks, you will see that this term of small signal model is used ubiquitously. So we will also refer to this as a small signal model. Now, before moving forward, it makes sense to understand what is the small signal equivalent of all the elements that we know of, right? For example, a resistor, right? Let's say we have this resistor. So what is the small signal equivalent of a resistor? So let me write this as this is the element and this is the small signal model. Right? So what is the small signal model of a resistor? How will you get the small signal model of a resistor? Note that how did we get the small signal model in the first place? We needed to characterize the element. So how do you characterize the resistor? A resistor is characterized by, if I have a voltage V across this element and you have a current I that is flowing in, the small signal, the relationship between I and V, right? The relationship between I and V is I is equal to 1 over R times V. So what will be the small signal equivalent of this? So note that the IV characteristics of a resistor is a straight line. And what is the small signal equivalent? The small signal equivalent, whatever this element might be, this is equal to 1 over del I del V, right, which is nothing but R, correct? So the small signal equivalent of a resistor is the resistor itself, and it makes sense because my resistor is a perfectly linear element. What about a capacitor? What about a capacitor? So when you see a circuit element that is a capacitor, what is the governing relationship between of this capacitor? Primary governing relationship is between the charge stored across the in the plates of the capacitor and the voltage across the capacitor, right? So the governing relationship is Q equal to C times V, right? So like the resistor, the governing relationship for a capacitor is again a straight line, right? So what is the slope of this straight line? So this slope is equal to 1 over r, correct? What is the slope of this straight line? The slope of this straight line is C, right? So the slope is C anywhere on this curve. So essentially this capacitor gets replaced by a capacitor with a value C. Similarly, if you have an inductor, right, which has a current I going through it, what is the governing relationship of an inductor? The governing relationship is phi is equal to Li, where phi is the flux, I is the current that is going through it. So essentially, if I sketch I here and phi flux here, again I get a straight line. What is the slope? Slope is 1 over L, right? So again this is a linear relationship. So inductor remains an inductor, no change, correct? What about a voltage source? What about a constant voltage source? What is its linearized equivalent? What is its small signal equivalent? So again, let's go back to our IV characteristics, right? What is the so let me call it VDC. So what is the IV characteristics of a voltage source? So voltage remains constant regardless of the current. So this is a straight line perpendicular to the x-axis. So what is the slope? Slope equal to infinity. So if I have to replace this with its incremental equivalent, what do? I replace it with an element which is 1 over the slope. So what is this element? What is this element? If slope is infinity, this is equal to 0, which means the impedance given by this element is 0, which means this is a short circuit, right? So this is a short circuit. Correct? What is it if I have a constant current source, let's say IDC? So again, let's go back to our IV characteristics, correct? So this is VDC here. We go back to our IV characteristics. What is the IV characteristics of a constant current source? Again, this is a flat line parallel to the V axis. So what is the slope? Slope equal to 0, which means 1 over slope is equal to infinity. So you have to replace this IDC with an element, right, whose del I del V is, or del V del I is infinity, right? So let me slope. So this is nothing but del I del V, right? So this is again del I del V. So since del I del V is 0, in other words del V del I is infinity, which means its incremental resistance is infinity. So you replace it with a open circuit, right? So this is A, this is B, this becomes A, this becomes B. A, this is B, see, this is open circuit. And in general, if we have a nonlinear element which has a current voltage relationship of I equal to F of V, right? I equal to F of V. We have to replace this nonlinear element with this incremental equivalent, which, I mean, if all the terms are real, right, and all the derivatives are real, then we'll replace this nonlinear equivalent with a resistor of value 1 over del F del V, right, around some operating point Vn, or I can simply write in the form of del I del V around some operating point Vn. Okay? Okay, does it make sense? Okay.